Construction and engineering are the sole backbones in our modern society. They are the foundation of our world's buildings. You are now watching our second podcast brought to you by Robert Knott, Zoe Alvarez, and Elizabeth Cordero in Architecture Technology. EPCC Spring 2025 with instructor Lundy Delgado, where we dive into the world of construction in our modern world.
Hi guys, I'm Zoe. I'm Elizabeth. Today we're doing chapter 14, which is about
Sitecast Concrete framing systems.
yes, and unfortunately we are missing Robert today. We do not know where Robert is at, but we will do what we can do.
So we're just waiting for you?
Yep, we're just waiting for Robert, guys. I guess.
There you guys are. I've been trying to find you guys since last episode. I was like going around the building. I ended up actually going to the wrong podcast. Like, what in the world just happened?
We've been here waiting for you.
This whole time? Dude, I couldn't even find you guys. What in the world?
Okay, well, this is Robert, guys. He made it. And what are we doing today, Robert?
Well, everybody, we're officially now going through chapter 14. And once again, just wanted to say thank you all for coming to this presentation where you learn the fundamentals of construction. Hello, everybody, and welcome again back to this podcast. I just wanted to real quick make myself appearance known. Yes, I finally found the camera again this time. I apologize for the less inconvenience. I wanted to real quick record this because I just wanted to kind of introduce myself again right before we begin this podcast again. So, we're going to be covering chapter 14, specifically this is Sitecast for concrete framing systems. This is going to be focusing on a lot of us discussing about concrete where we do today's podcast. Do be warned though, but today's podcast might have a few crazy things that you guys may have to expect as you kind of go on, but yeah, that's why we're going to be here guiding you on this journey. Welcome to Late Night Studio at the Architecture Z building. Now, before we start this, I'm just going to be going back to work and finishing up my usual stuff. Excuse me if you don't mind me. Let me just get back to work on my architecture stuff. Robert, how about you show everybody where concrete is located? Sure thing, Robert. Now here, let me tell you where concrete is located. It is in the sidewalks of our city. Concrete is also in our houses. It's in the barriers of our streets. It's also right on the corner of the Z building. It's in the makerspace.
Dude, are you still talking about concrete?
Yes, I am.
He likes concrete, leave him alone.
Hey,
What's
bro,
wrong
chill
with that?
out.
Yeah.
So yeah, you get the idea. Concrete is everywhere. How about now we tune into our podcast where you learn the educational technicalities of concrete.
Hello. So we're going to be presenting chapter 14, Sitecast Concrete framing systems. And the first subtitle is casting a concrete slab on grade. A concrete slab on grade is a flat surface of concrete that sits directly on the ground. It is commonly used for roads, sidewalks, patios, airport runways, basements, and ground floors of buildings. A slab-on-grade floor usually experiences minimal structural stress, mainly just a direct compression from the loads above, pushing down into the ground. This makes it a straightforward example of how concrete is cast on site. As for subgrade preparation and edge forms reinforcing, to prepare for a slab-on-grade, unstable topsoil is removed to expose the subsoil, and if the subsoil is too soft, it's compacted or replaced. A 4-inch layer of 1.5-inch crushed stone is added as a capillary break layer to keep moisture away. For slabs without surrounding walls, a wooden or metal edge form is built around the perimeter and coated with the release compound to prevent sticking. The form is leveled to guide the slab surface during pouring. When surrounded by walls, an isolation joint with filler materials is added to allow movement, and the slab thickness ranges from 3 to 4 inches for residential and 6 to 8 inches for industrial floors. A vapor retarder, usually a heavy plastic sheet, is placed over the stone for interior slabs to protect ground moisture. For reinforcing, a reinforcing mesh that is cut slightly smaller than the slab is placed over the vapor retarder or crushed stone. Reinforcement is commonly used for lightly loaded slabs in houses, such as 6x6 W1.4 times W1.4 mesh. As for factories, warehouses and airports, heavier wire fabric or reinforcing bars are used to prevent cracking from shrinkage, temperature changes, and other stresses. Fibrous microfibers can also be used for additional reinforcement, which are synthetic fibers added to concrete to improve its strength and durability. Pouring and finishing the concrete is a process of casting a slab on the grade that begins with placing wet concrete into the formwork. Workers then spread it out using shovels or rakes and use tools or an immersion vibrator to remove air pockets, especially around the edges. If the welded wire fabric reinforcing wasn't set on chairs or supports, workers use metal hooks to lift it to the slab's mid height, positioning them to resist tension from forces above or below. They then strike off or screed the concrete by dragging a stiff plank across the formwork's top edges, level the surface, and this is done with a sawing motion to avoid pulling coarse aggregate from the surface, maintaining a bulge of concrete in front of the screed plank to fill any low spots. After the concrete is poured, the initial step is to float it using tools like bull floats or derbies to level the surface. This process helps to flatten and consolidate the concrete. Once the concrete begins to stiffen and the bleed water, which is the watery sheen on the surface, then evaporates, and the slab is then floated again. For larger areas, rotary power floats are often used. The second floating step is crucial as it further consolidates the surface and brings up the cement paste, which is then smoothed over the coarse aggregate and any low spots. It's important not to overflow as this can cause too much paste and free water to rise, leading to puddles and poor finish. For a completely smooth, dense surface, the slab is troweled right after the second floating. This is done by hand using a smooth rectangular steel trowel or with a rotary power trowel. If the mason can't reach all areas from the edges, they use plywood squares called knee boards to kneel on the concrete without making indentations. Marks left by the neighbors are smoothed out as the mason works backward across the surface. So if a non-slip surface is needed, a stiff bristled push broom is drawn across the slab after troweling to create a textured broom finish. If a concrete slab needs to meet strict floor flatness standards, it may be restrained after each floating or troweling step. This is done using a flat bottom straight edge about 10 feet long, which is drawn across the surface of the slab to remove any minor bumps or dips created during floating or troweling. Take-on hardeners, which are dry powder that react with concrete, are sprinkled on the slab between screeding and floating. They harden surfaces for places like warehouses and factories. When the finishing operations are completed, the slab is cured under damp conditions for at least a week to prevent cracking or dust from premature drying. This can be done by covering it with damp materials like sawdust or burlap, using an impervious sheet, or spraying it with a liquid curing compound to retain moisture. Since no concrete floor is perfectly flat and normal finishes creates undulations that are usually unnoticed, so for ordinary slabs, flatness is specified by the maximum gap under a 10-foot straight edge, typically 1/4 to 1.5 inches. So industrial warehouses need super flat floors, measured using F numbers for precise flatness and levelness. Laser-guided automatic machines also help achieve the high accuracy needed for these super flat floors. Managing cracking, the concrete slabs are thin and not heavily reinforced, so they can crack easily. The cracks happen because the concrete shrinks as it dries, expands, or contracts with temperature changes, or moves differently from nearby structures. This can affect how well the slab works as well as making it look bad. To prevent or control cracking in the slabs, joints are added to create a neat pattern for cracks to follow. These contraction joints are intentionally weaker spots in the slab that help relieve tension from drying shrinkage. They can be made by grooving the concrete while it's still wet or by sawing it after it hardens. The spacing of these joints depends on the slab's thickness and shrinkage range. Normal slabs are 4 to 8 inches thick, needing joints spaced about 11 to 17 feet apart. It's best to arrange the joints to form roughly square panels. Isolation joints, also called expansion joints, are used to separate the concrete slab from other parts of the building. These joints are made by placing full depth materials, usually half to 1 inch wide, into the slab. They allow the slab to move freely due to temperature changes, structural loads, or ground movement. Isolation joints are typically placed where the slab meets the walls, curbs, columns, or load bearing. They can also divide larger regular slabs into smaller sections to reduce cracking. So to reduce the cracking, the concrete mix can be adjusted to minimize drying shrinkage, making the concrete stronger and more resistant to cracks, even though it's more expensive. Special types of cement can be used to counteract shrinkage, allowing for large slabs without contraction joints. And adding more reinforcing or fibrous materials to the concrete mix helps prevent cracking. It protects the slab from drying too quickly while it cures, ensuring full strength. Another method is post-tensioning, which tendons are used to compress the slab, reducing the need for conventional reinforcement.
So then, when we will be talking about casting a wall, commonly reinforced concrete walls at the ground level rest on a concrete strip footing. The footing is formed and poured similarly to concrete slabs on grade. A groove, known as a key, is sometimes formed at the top of the footing with strips of wood that are temporarily embedded into the wet concrete. Additionally, dowels consisting of steel reinforcing bars are also installed into the footing and are later overlapped with the bars in the walls to form a structural connection. Furthermore, wall reinforcing can either take the form of one vertical layer of horizontal and vertical bars at the center of the wall of two layers closer to the faces of the wall. L-shaped horizontal bars are installed at wall corners to maintain continuity between two portions of the wall. If the top of the wall connects to a concrete floor and another wall above the bars, if the top of the wall connects to a concrete floor or another wall above, the bars are left protected from the formwork and will later be embedded in a later pour of concrete. Additionally, wall forms can be custom built of lumber and plywood for each job, but are composed of prefabricated panels. These panels are corded with the form release compound set on the footing, aligned and braced with the form ties. Form ties are small diameter steel rods shaped to hold the formwork together under the pressure of wet concrete. The form ties are inserted through holes in the formwork panels and secured to the back of the form by devices supplied by the ties. Once the ties are in place and reinforcing has been inspected, the formwork from the second side of the wall is erected. The wallers and braces are added, and the forms are inspected to ensure they are straight, plumb, aligned, and adequately tied and braced. With the transit or laser leveling device, it's used to establish the height at which the concrete will be poured. Once the height is established, it's marked around the inside of the forms and ready for the pouring of concrete. Evidently, concrete is delivered to the site, workers stand on planks at the tops of the form and pour the concrete into the forms, consolidating it with a vibrator to eliminate air pockets. Once the form has been filled with concrete to the desired height, hand floats are used to smooth and level the top of the wall. Once the flat top is achieved, plastic sheets or canvas, letting the wall to dry. During and bracing, the wallers are taken out, connectors are removed, and the framework is stripped from the wall, leaving the form tie-ins. The ends are twisted off with heavy pliers, and the form tie holes are filled with grout. During this process, defects of the wall surface can be repaired. Once this process is complete, the wall is complete. Similar to slabs on grade, shrinkage, cracking, in Sitecast concrete walls is managed by contraction joints in wall openings or where changes in wall height and thickness occur. Isolation joints are also used where cast concrete walls meet other structural elements. Take it away, Robert.
All right. Then let's take it away. Thank you so much for the microphone, Zoe. Now let me get to my part real quick. So now we're going to be talking about this next part of the chapter called casting a concrete column. So if you think about it, we went from concrete walls to concrete columns. What's the difference? Well, concrete columns are formed with cast much like a wall, with a few more important differences. So the footing is usually an isolated column, putting a pile cap or a casting rather than a strip footing. The edge of the column reinforcing is assembled with wire ties and hoisted into place over the dowels. And no, not like the way I was talking to my cat. I apologize. The space is too tight in the region where the vertical bars and dowels overlap. The balls may be spliced end to end with welds or mechanical connectors instead. So the column form may be a rectangular box of plywood or composite panels, a cylindrical steel or plastic tube bolted together in halves so that later it can be removed, or a wax cardboard tube that is stripped after curing by unwinding the layers of paper that make up the tube. So unless a rectangular column is very broad and wall-like, form ties through the concrete are not required. The vertical bars project from the top of the column to overlap or splice to the bars of the column for the story above, Are the bends over at the right angles to splice into the floor or roof structure above? Or vertical bars overlap the tops of the bars from the column below or offset, of course bent inward, by 1 bar in diameter to avoid interference?
Our next topic is one-way floor and roof framing systems. So one-way solid slab spans across parallel lines of support provided by walls or columns and beams. The forms for girders, beams, and the slab are built continuously and poured at the same time as a single piece. Temporary framing and shoring are made of metal or wood that supports the formwork and must be strong and closely spaced to handle the weight of uncured concrete. Formwork is designed by structural engineers to ensure safety since failures can risk the workers and the property. So to create beveled or rounded edges, shaped strips of wood or plastic are inserted into the corners of the formwork. This prevents sharp edges from breaking off during stripping and reduces the risk of damage to people and furniture. A form release compound is applied to the formwork, and then the reinforcing bars are added based on the engineer's plans. After checking everything, the girders, beams, and slab, they are then poured together and sample cylinders are taken to test the concrete strength. One-way slabs are usually 4 to 10 inches deep, and the top is smoothed with a steel trowel and covered to keep it damp while curing. The only parts left sticking out above the slab are the opposite column bars that are ready to connect to the next floor's column bars. The formwork is cleaned and moved up for the next cycle of forming, reinforcing, and pouring. Once the slab and beams are strong enough, the formwork is removed and the slabs and beams are supported with props until they get stronger. This exposes the underside of the slab for the installation of other work such as plumbing or sprinklers. The best concrete beam is usually 3 times deeper than wide. One-way solid slabs are sometimes supported by slab bands, which are much wider than they are deep. This method saves concrete and steel because the wide slab bands reduce the span between them, allowing for a thinner slab. Also, the shallower slab bands compared to regular beams mean that the building's story height can be lower, saving on columns, walls, and vertical piping and ductwork. For one-way concrete joists, also known as a ribbed slab, they get longer and the slab needs to be thicker. A ribbed slab is used instead where the bottom steel is in spaced ribs, also known as joists. The thin slab on top of the joist is only reinforced with shrinkage temperature bars. This system uses concrete efficiently, allowing it to span longer distances than a one-way solid slab. Each joist acts like a small beam, but usually doesn't need stirrups because a narrow joist space is enough. The ends of the joists are widened so the concrete can handle the diagonal tension or shear forces. Joists are made with metal or plastic pans on a plywood deck. They come in 20 inches and 30 inches in width and can be up to 20 inches deep. The pans taper for easy removal since you can adjust the joist width by changing the spacing of the pans. The plywood forms the bottom and special end pans widen the joist's ends. After applying a release compound, reinforcing bars are placed and then concrete is poured. Joists are supported by broad bands that match their depth, simplifying the structure and maintaining a uniform ceiling height. Wide module concrete joists is when a building codes require a slab to be 4.5 inches thick or more fire resistance. The slab can span longer distances than usual. In this case, a wide module or skip joist system is used, with joists placed 4 to 6 feet apart. This method originally used wood strips to block out concrete in every other joist space, but now special pans are made for wider spacing. Wide module joists have to support about twice the weight of regular joists, so stirrups are needed near the ends. If regular U-shaped stirrups are used, they must be installed diagonally to fit in the narrow joist. Single leg stirrups can also be used to support the joists. With designing one-way sitecast framing systems, this involves using rectangular floor plans where spans are typically up to 20 feet. For these spans, one-way solid slab construction is economical. For longer spans, one-way solid slab with slab bends or one-way joist systems can be used. When floor loads are very high, one-way slab and beam systems are suitable. These systems are also effective for resisting lateral forces from wind and earthquake due to their deep column-to-slab connections, which provide greater resistance to rotational forces.
So, how fun.
You know, the other day I was trying to tell my friend a concrete joke, but it was over dry. It's not funny. Sorry, that was
Did you really tell it, or was that like on us?
Dude, I was trying to quickly try to find a joke so I could try to put it in the podcast.
Okay, so next we're gonna talk about a two-way concrete framing systems, which are used where columns supporting a slab can be arranged in bays that are square or nearly square. A two-way solid slab system is rarely seen, but occasionally used for heavy-loaded industrial floors. In heavy-loaded industrial floors, the slab is supported by a grid of beams running in both directions over the columns. However, most two-floor and roof framing systems are made without beams. Most systems consist of the slab being reinforced in a way that the stresses in the different zones of the slab are accommodated within the same thickness of concrete. This simplifies the form of construction and reinforcing bar patterns. An example of this type of framing includes the two-way flat slab. Its formwork is completely flat except for the thickening of the concrete to resist the forces around the top of each column. The thickening was originally accomplished with a funnel-shaped mushroom capital and a square drop panel, but today the capital is eliminated to reduce the formwork cost. Typical depths for the slab itself range from 6 to 12 inches. Reinforcing for a two-way slab system is laid in both directions in half-bay wide strips of two types, column strips and middle strips. Column strips are designed to carry higher bending forces in the zones of the slab that cross the columns, and middle strips have a lighter reinforcing pattern. Since concrete is already reinforced in both directions, shrinkage temperature steel is not needed in two-way systems. The drop panel and capital have no additional reinforcing besides what's provided by the column strip. An additional system includes a two-way flat slab system. The typical slab depth can range from 5 to 12 inches and is found in more lightly loaded buildings. The slab does not need to be thickened over the column. The system makes the formwork simple and allows for columns to be moved to improve floor plan arrangement. Additionally, the flat ceilings in the system allow for room partitions to be placed anywhere with the ease, and the absence of beams or grinders allow for minimal story heights. The zones along the exterior edges of the two-way flat system and the two-way flat plate system require special attention. The slabs in these systems can be cantilevered beyond the last row of columns at a distance equal to 30% of the interior span. If exceeding the slab is not possible, additional reinforcing must be added to the slab edges to carry the higher stresses that will result. Since a two-way flat plate has no drop panel, additional reinforcement in the slab at the top of each column is required. The additional reinforcement can be accomplished with added reinforcing bars or other special design reinforcing. Furthermore, a two-way waffle slab, also referred to as a two-way concrete joist system, is a two-way system that is equivalent of the one-way concrete joist system. In this system, metal or plastic pans called domes are used as formwork to eliminate non-working concrete from the slab, allowing larger spans than with the two-way flat plate. Joists are spaced 36 to 60 inches at center in depths of 24 inches. Concrete heads serve the same function as a drop panel in the two-way slab system and are created around the tops of columns by leaving the domes out of the formwork in these areas. Finally, when designing two-way sitecast framing systems, it is important to consider the loads. For light loads, two-way flat plate is the most economical, but where loads are heavier or lateral resistance must be developed, a two-way flat slab is a better choice. The most expensive system is the two-way concrete joist system. However, it can span the farthest and support heavy floor loads. Lastly, two-way joist systems are occasionally used where its unique advantages justify its high cost.
And now let me just bring this right back. Now we're going to be talking about our next part of the chapter. So we're going to be talking about sitecast post-tension framing systems. So post-tensioning can be applied to any of the sitecast concrete framing systems, which they're mostly commonly used in beams, girders, and slabs. One-way and two-way, to reduce member sizes, reduce deflection, and extend spanning capability. Two-way flat plane structures are very commonly post-tension, especially when spans are long or restrictions on the height of the building require minimal slab depths. The tendon layout, however, is quite different from the conventional reinforcing layout. Shown in the figures, of course, conventional reinforcing, instead of being placed identically in both directions. The drape tendons are eventually distributed in one direction and banded closely together over the line of columns on the other direction. This arrangement functions better structurally in post-tension slabs because it balances the maximum upward force from the banded tendons against the maximum downward force from the distributed tendons. It's also much easier to install than distributed drape tendons running in both directions. If the structural bay is square, the same number of tendons is used in each direction. The pre-stressing force from the banded tendons becomes eventually distributed throughout the width of the slab within a short distance of the end anchorages because of the action in the concrete. Now we're going to be taking a podcast break. We're going to see what Robert does when he tries to learn, is concrete porous? Let's find out after this short break. What we can also learn, concrete is also very porous. How will we test it out? Let's see how Robert does this. No, not like that. You can't throw bottles of water on the spot. Get that water jug out of here, gosh darn it. Excuse us. Let's check back in with Zoe, Elizabeth, and Robert to see what kind of things they're learning in the video. We are now finally back, everybody. Back to the podcast. We again apologize for the inconvenience. Robert didn't know what he was doing. Let's get back into rolling, shall we?
Our next topic is other types of Sitecast concrete. As for tilt-up construction, it is a process where reinforced concrete wall panels are cast lying down over a previously poured slab that acts as a smooth work surface. This method eliminates most formwork and costs usually needed for Sitecast concrete walls, making it economically favorable for single-story buildings. Once the panels have cured to sufficient strength, they're lifted into a vertical position and hoisted by a crane, and then are grouted together. While most tilt-up constructions are walls up to 45 feet, it's possible to have walls as tall as 100 feet. They can also be designed as sandwich panels with rigid plastic insulation for improved thermal efficiency. For insulating concrete forms, also known as ICFs, they serve to contain the concrete when the wall is poured, which stays in place as part of the wall and also acts as insulation. They are light and easy to assemble and support both horizontal and vertical reinforcing bars. They come in shapes like polystyrene, foam blocks, or foam plastic planks. Forms are braced during concrete pouring to prevent movement, and the concrete is poured into the forms, sometimes in layers if needed. ICF walls have good thermal resistance ranging from R15 to R30 and are soundproof and impact resistant. Additionally, finished materials are added to protect the foam from damage and weather. For shotcrete, pneumatically placed concrete which is sprayed into place using compressed air from a hose. It has a low slump, so it can be applied to vertical walls with minimal formwork, but it needs a solid surface to spray against. Jacqueline is used for foundation walls, stabilization of steep slopes, repairing damaged concrete on the faces of beams and columns, seismic retrofits, and for the production of free-form structures such as swimming pools, skate parks, and other play structures. Architectural concrete is most formed concrete surfaces are strong but often have many blemishes and irregularities due to standard construction practices. If the concrete is meant to be a quality finished surface, it can be made to higher standards known as architectural concrete, which this involves specifications that control things like flatness, textures, color uniformity, and the appearance of formwork, as well as the size and quantity of defects and details of joints and corners. There's many options for surface treatment, such as using rough boards in the formwork to create interesting textures on the concrete surface, and other materials can make the concrete smooth or give it different patterns like ribs or veins. After the concrete has partially cured and the forms are removed, you can expose the aggregate by scrubbing or hosing the surface. You can also shape the fresh concrete using abrasive stones, grinding, or hammering with special tools. You can also add colors, dyes, paints, and sealers to the concrete to enhance its appearance. and protect it from weather, dirt, and wear. Pavings, toppings, and other uses. Precast concrete is used in many ways in building construction. It's great for making pavements and curbs, creating raised platforms for equipment, covering metal or precast concrete decks, and filling metal stairs pans, and even building entire concrete stairs.
So we're going to be talking about concrete, stone, and masonry. These materials are necessary. It's commonly necessary to cut hard materials in the course of obtaining, processing, and construction itself. In pre-industrial times, hard materials were cut with hand tools such as steel saws, hardened steel drills, and wedges and explosives, which were placed in drill holes and then were used to split off large blocks of material. These techniques and tools are still used to some extent today, but diamond cutting tools are used for tough cutting in the construction industry. These diamond tools and techniques include a diamond saw, a diamond circular saw, stitch drilling, a water-cooled walk-behind flat saw, a sawed and drilled opening lines. Diamond tools are expensive, but they cut more rapidly and cleanly and last longer, making them more economical. These tools can also have better performance than other conventional tools, such as precision sawing marble and grinding into thin sheets for floor and wall facings. Diamonds are able to cut hard materials because they are the hardest known material. The diamonds that go into cutting tools are synthetic and produced by exposing graphite, and catalyst to extreme heat and pressure. The sorting and grading the small diamonds results. The choice of diamonds and the composition of the bonding matrix when manufacturing the tool are chosen by the type of material to be cut. Some tools are designed to cut dry, but most are used with a spray of water that cools the blade and washes away the waste material. Cutting tools based on materials other than diamonds are still common in construction, such as circular saw blades composed of various abrasives. Those precise tools include the pneumatic jackhammer, hydraulic splinters, and sledgehammer.
So our last topic will be uniqueness of Sitecast Concrete, and this involves the ongoing development of high-strength concrete and reinforcing, along with better concrete forming and pumping tech, has kept Sitecast concrete construction competitive with structural steel for all kinds of buildings. The Burj Khalifa is a great example since it is 2,720 feet tall and made mostly of steel, reinforced Sitecast concrete. Self-consolidating concrete, which is as strong as 14,000 psi, was used in its construction too. Concrete is a flexible material that is shaped by designers and can be used in almost any building type and scale. It's a powerful material that needs skill and imagination to be used well to avoid boring results. For cost saving, designers can use standard framing systems, but as for creativity, they can try new shapes and textures. Some designers focus on its sculptural potential, others on surface patterns, and some on structural logic. This has led to great works like Le Corbusier's chapel at Ronchamp and Wright's Unity Temple, as well as the designs of Torroja, Candela, and Nervi, which were also built economically. We're done.
And that has been the Architecture Technology Podcast. Just wanted to say thank you all for finally tuning in, and I appreciate y'all listening to us talk about a lot about concrete today. And make sure to leave a like, subscribe, and I'll see you guys in the next podcast on episode 3, where we cover chapter 22. Thank you all for tuning in, everybody.
Thank you, guys.